So this is the next topic that we want to move on to. So this is basically theory. Each phase are separated spatially by 120 degrees apart. Yeah. And then obviously you have your Y configuration and delta configuration. And our star configuration, sorry, has a start point or a neutral point, right? So, okay. Yeah. And then the delta have no common to no neutral line, right? Then well, this is theory, three phase. The advantages of transformers. You have a question that asks you all why use a single phase transformer over a three phase transformer? And this is basically the answer here. Right? Right. This is the connections here. Here's connections. Excuse. Right? So here now is your Y configuration analysis, right? So for a line, your is your line voltage is equal to root 3 times your phase voltage. Line and phase currents are the same for a Y configuration. But your voltages, your line voltage equals to root 3 times your phase voltage, right? And for a Y, the phase voltage lags the line voltage by 30 degrees. So let me see if you are seeing that. So VAB is your line voltage and VAN is your phase voltage. So the phase voltage, which is this, lags the line voltage by 30 degrees. You understand? So say if the phase voltage was here, it will lag the line voltage by 30 degrees. Or you could also say the line voltage leads the phase voltage by 30 degrees. You see the line voltage here, phase voltage is leading because the angle is positive here, right? Right. This is basically it for a Y configuration. Any questions on this so far? Or you all cool with this? You all cool? Okay. Right. The delta configuration um, is basically the inverse or the opposite for our Y. So in this case, the delta, the line and phase voltage is equal, but the line current is equal to root 3 times the phase. Right? You see the difference? For the star, the line and phase currents are the same, while delta is not. For the delta, the line and phase voltages are the same, while the star configuration is not. Right? And for delta, your phase currents, just IA, phase current, and then you have your line current. Right? So your phase current leads the line current by 30 degrees, or the line current lags the phase current by 30 degrees. You see the current. But really how they draw this here is that like is really you take the line current as a reference and draw it. Right? But in this case they're saying that um if you watch it here you could think this as the line current, let's say phase current. So your line current will lag your phase current by 30 degrees. Yeah. Right. You'll see how this applies when I actually do an example, right? I know it's something kind of confusing now, but when you actually do an example, you'll see how where this really comes into play. Right? Also, I think you had a question that's in your post lab, I think. It's a proof for the mutual current is zero for a balanced system. Yeah? And for a balanced system, now Y configuration, your phase and line currents are the same, right? And each of them are spatially 120 degrees apart because of that balanced system. So if when you add up all your currents, noting your angle you will get 0, right? If you add I phase 0, you can just plug in a value. If you put 1 angle 0, 1 angle minus 120, 1 angle plus 120, you will get 0. Yeah? So that's to prove if your neutral current, if they ask that question, how to prove neutral current equal to 0 for a balanced system, this is what you're going to choose. Some three-phase formulas, so let's summarize the formulas here for you all. You can see that there. Right. So since we constrain time, I'll just run through the calculations here, right? So this is past paper 2025. They said that, you're looking at, let's say, you have university factory engineering, blah blah blah. I want to look at the real thing they give me. Me want to all them kind of fluff things, right? So they say building receive 480. The building receiving a 480 volts star connected three-phase supply. Where they want to know. They say that the machines and stuff require 230 volts three-phase supply. Okay. We have decided to utilize 3 single-phase dry-type transformers to step down the building's incoming supply to a 230 volts delta connected supply for the building. Right? So you're basically going to have a star delta configuration. So you have a star on your primary side and you have a delta on your secondary side to step down the voltage to 230 volts delta connected. Yeah. Right. And then you say that the load here now, the machinery, you can model the load as 0.5 ohms in series with our inductance, 0.6 ohm. Right? So you have to find the phase voltages and etc. Yeah? So this is what the load will look like here. Right? You have your resistance and series with our inductance. And this is what we did in the three-phase law. Right? You basically put the resistor in series with the inductor. Right? You all remember that? That is what we did in the lab. So it's the same kind of configuration here. Right? So the R will be what? The 0.5 ohms and the inductance will be 0.6 millihenries. Right? And the system will be, as I said before, a star delta configuration. Yeah? Right. So we need to find the phase voltages for the star connected loop. Right? So remember that we receive a delta supply, right? But this is a star connected load. So we need the number for a star configuration. Your line and phase voltage are not the same. Your line and phase currents are the same, yes. But your line and phase voltage are not the same. Your line and phase voltage are the same for delta configuration. So to find the phase voltage for star configuration, you're taking your line voltage divided by root 3. And you're going to have that angle of minus 30 degrees because remember the phase voltage lags the line voltage by 30 degrees. Right? So when you do the calculation, the 230 angle 0 over root 3 angle minus 30 degrees. You'll get this as your phase voltage. Phase star configuration. Same for your B phase. Remember, you're noting the spatial angle that is separated by, right? For delta is what the line voltage is spatially separated by 120 degrees, right? The same thing here, one is higher minus 120 and higher plus 120. I have obviously have your minus 30 degrees, that's your phase voltage lags your line voltage by. And the next angle, same thing with the C phase, the same thing, and get the angle. Right? Any questions on that? Everybody clear? Or you do understand? Everybody good? You all understand what went on there? Yes? No? Maybe? No one answer.
You could just run it through one more time, please.
All right, cool. Right. So now we have a delta connected secondary, right? And the delta connected secondary is connected to a Y connected load, right? This is the load here, right? And we want to find the phase voltage in the load, right? So remember the load is a Y configuration. So obviously you're not going to be the phase and line voltage not going to be the same for a star connected load because line and phase currents are same for a star, but line voltage equals to root 3 times the phase voltage, right? So to find the phase voltage for the star connected load will be your line voltage on root 3. But you also need to consider the angle difference between your phase and your line voltage. Yeah. So
Right.
the
Okay.
phase voltage, yeah, so the phase voltage lags the line voltage by 30 degrees. Yeah. So remember your line voltages are coming into your supply for your load, right? And that is from your delta supply, your delta connected secondary. And remember, your line and phase voltage are same for delta, and they are separated spatially 120 degrees apart. Now you have your line voltage is 230 angle 0. Then you have your B phase is 230 angle minus 120, and your 230 angle 120. Yeah? And then obviously you have to consider your angle here as well. That the phase and line voltages lag phase star. Yeah? And when you do your calculations, you should get your magnitude and your corresponding angle. Yeah. And once again, this is polar form, right? Yeah. You all understand now?
Yeah.
Alright, cool. So now we have to find a line current between the transformer and the loop, right? So basically, the current are going to be flowing through the lines between the transformer and the load, right? There's the transformer and the load here, right? It's going to be the current flowing through the load, right? Because this is per phase, you're going to have a current flowing through the load in one phase, flowing through the load in the next phase, and so on, right? So we need to find the load impedance, and that will be the per phase impedance, right? You can just find for one phase, R and L here, right? So they give us the resistor, give us the XL, give us the inductance, sorry, where to find XL. So between R plus JXL, or you could say R J omega L, and they give us the frequency at 60 hertz, and we calculate the inductance and stuff here, right? And you get your total impedance to be 0.504, 0.68 ohms. Yeah. And this is once again polar form. Polar form easier to work with, typically in when it's solving three-phase systems. So I would recommend you stick to polar form, right? Nice. I'm gonna find the line currents. So for star configuration, your line and phase currents are the same, right? So to find your line current or your phase current, you basically take your phase voltage that I calculated before, right? Divided by your per phase impedance, right? And then you get this. You look at angles, remember, you have your angles from before. You make sure you use your angles, and you use the angle for your load as well. When you do that division, you should get your corresponding line of phase currents. Yeah, straightforward, that's simply enough, right? So I want you all to try this as well. Once the session is over, try it. Let me know if you're getting the values. And if you get problems, let me know. I'll try to see if I can assist you. Yeah? Is everybody cool with this, right? Yeah? Alright. Nice. So you want to find the phase current in transformer secondary winding now. So remember the transformer connected to our delta on the secondary side. Right? So Remember, for delta, the line of phase voltage are the same, but the line of phase currents are not. Your line current equals to root 3 times your phase current, right? So to find your phase current, you're taking your line current divided by root 3, and delta, the phase current leads the line current by 30 degrees. Right? So you're taking your line current you calculated before, plug in it in here, divided by root 3, and include the angle 30 degrees. Right? When you do that calculation now, you'll get a corresponding values. Right? So the only way to remember this is actually doing the question and applying it. Right? Looking at it, you're not going to remember anything. So I want you to, after session, go and try the question, apply it, look at the theory, you will get the presentation at the end of the session. So you have the presentation to look at to reinforce the theory and try the question. Cool? Everybody understand? Yes?
Yeah. Yes, sir.